Hello. So my name is Javier Bravo, and I work at NAITEC. So NAITEC is a technological center in Spain. It's divided into 4 business units: mobility, mechatronics, technology services, and then new businesses. It's divided into 6 wider knowledge areas that are here. You can see them. We have 3 different buildings in 3 locations in the province of Navarra in Spain, doing different things and essays to different clients from the industry, local industry. These are some of our partners, but there are many clients that are not here. But I'm specifically talking about printed electronics that we've been doing since 2004, where we started in functional inkjet printing. From the beginning, we wanted to work with the industry, and printed electronics seems for us to be a very interesting field. Throughout the years, we have been part of the development of 2 startups, one that still is producing inkjet systems for companies, pharma companies in the region. And in 2017, there was a second startup, Mateprints, that was industrializing inkjet and screen printing ink formulations for the market. Throughout the years, we've been helping many of our industrial partners doing many different devices. So with these 2D printing technologies, you can add new functionalities to different parts and different materials. You can print circuits on textiles. You can print circuits on plastics, metals. You can add heaters to surfaces that before was much more difficult to have them, capacitive sensors, antennas, and many more. And also, as a natural evolution of 2D printed electronics, we started working on 3D printed electronics. And for this, we have 3 different approaches. On the top left, you have in-mold electronics. So you start with a traditional 2D printed circuit on a thermoplastic. You need special inks that will withstand the deformation of the plastic, and then go to a molding process so that you can have a conformal circuit for sensors or whatever electrical circuit that you need in your component. It will be embedded in a molding process. The second approach that we've been working with is at the bottom on the left, and this is a 15XBT system from NAITEC that allows us to add, in this case it's a capacitive sensor, but we can add circuits and components into 3D pieces. We can even create them from 0 because it has a filament extrusion module, so we can create the structure and then add the circuits and the components with a pick-and-place system. This is very interesting approach for 3D printing electronics. And then the third one is incorporating new materials to already traditional 3D printing technologies like the FDM, like the filament that I'm presenting today. So we were working on formulations for new filaments with special properties, like conductive properties, magnetic properties, and other properties. And this time, I'm talking about one of the conductive filaments that the team in NAITEC developed. The base polymer is ASA. This is a very interesting polymer for the industry because it has a very good durability in outdoor environments. It has good mechanical properties, and the printability is very good. So it can be used in sectors like automotive and electronics, for example. And in order to obtain a conductive filament from this material, this is more or less basically the process that my coworkers follow to functionalize it. So first, they need to dissolve the polymer in order to incorporate the metallic particles that will give the conductive properties to this material. Second, when all the mixture is homogenized, the polymer is, the solvent is removed from the mix, so we have a hard mixture of polymer and particles that's breaking down into small pieces. And then in the second step, we do the filamentation. So first, we use twin screw extruder to obtain some pellets, and then feed 3D EVO filamenter with these pellets. And finally, we obtain a filament that has very good conductive properties. So in this process, there are two properties that are one against the other. For the conductivity, we would like to add as many metal particles as we could. And actually, if it was directly metal, it will be ideal. But then it will be rigid and it couldn't be printed. So we need to find the compromise, the balance between the number of particles and the amount of polymer that's still in the filament. So after a huge number of experiments and some optimization processes, they have found a combination of copper and silver nanoparticles, microparticles, and also flakes. That is over 60% of the mixture with the polymer to still be able to filament this material, and that has the best conductive properties from all the tests. The result is a filament that before printing has a 6 milliohms centimeter. This measurement is being done with a 12 centimeter fragment of the filament, and we have followed a similar procedure to other filaments already commercial that are in the literature. They characterize the filaments like this, so that we can compare with the filament. And actually, I think our filament is state of the art. I think it may be better. After having the optimized formulation, we also study the parameters for printing, different temperature and speeds to guarantee the best conductivity of the final samples. And these are the conditions that we found to be optimum: 260 degrees and between 3.5 and 4.5 millimeters per second. And the resistivity that you see here is without post-treatment. Another approach is to load the filament with a lot of metal particles and then remove the polymer with a high temperature process or whatever. But then you can only print one material, or at least you need to print all the materials that you print. They need to resist this thermal treatment. So in our case, the idea is that we can print this material, and it's already conductive, together with the polymer, the base polymer, so that the electronic devices, they have also the conductive part embedded into the structural part. After we have found the best conditions for printing, we started doing some functional characterization. We wanted to know how much current this filament can withstand, because having a polymeric part is critical, and it might degrade with high current due to temperature. And we have tested it, and we can see that with currents of up to 1.5 amperes, the resistivity of the material doesn't change, so it's still functional as printed. So if the current is over that, the resistance starts to increase, so the material is being damaged. But we are happy that the current that this material can withstand is quite high, actually, for polymer-based filament. Continuing with the characterization, we fabricate some demonstrators to see that this filament is actually functional. So we have fabricated a lot of capacitive sensors, integrated into different pieces. Also, of course, tracks for circuits. We have also printed inductive coils, and you can see the red LED is lightened up with energy that is transferred non-contact with a contactless charging system, and we are capable of receiving enough energy from this 3D printed coil to light up LED. And also we have printed horn antennas with FDM and this our filament, and we have characterized this in an anechoic chamber. And the performance of the printed antenna is actually quite good. Even the antenna people who helped us in this characterization were surprised. They were expecting much more losses due to the plastic and the inhomogeneity and the roughness, surface roughness that it might have. But here you can see the results compared to a commercial antenna, the same type, and performance is practically the same. It's really, really good. And the weight is 4 times lower. So that's an important reduction of weight for an antenna that can be important in applications like space or drones or many other applications. This antenna is at the 3D EVO stand in the hall, 12.1, so you can actually see it. And you can also see this other demonstrator that we have fabricated. This is a brushless motor from a drone that we actually extracted from a real drone to prove that our material can be used for conductive current. So it's not that you have to believe what I said before. You can actually see it. And this is in the 3D EVO also stand. You can go there and see it work. There are 3 tracks printed in different sizes of this arm to prove that this is actual 3D printing. It's not using a 3D printer for 2D printing. We did different shapes in different sizes to prove that even if it's triangular or if it's a square, it still conducts electricity, and all of the arm, the 3 different paths, are well balanced in resistance so that the engine works properly. So you can see now a video, and there is a little LCD screen. You will see the current flow measurement there, and you can see how 1.2 amperes are flowing through the tracks, and the engine. Okay, I think it will start. Yeah. So if you see the number where current, you see the current that is going through the tracks. And so that's it. That's the material and how it works. And if you have any questions, I'll be very happy.
What is does the material affect how small a detail, how fine a detail you can produce, or is that just down to the printer, to the nozzle, to the existing technology?
Well, materials that have higher load of solids usually require higher diameter in the nozzle. So it's recommended to print like 0.6 or higher diameter, not like that. Maybe the standard one is 0.4. So you might need to increase a little bit the diameter of the nozzle, but not really dramatically.
Okay. So roughly the standard kind of equipment, extrusion equipment.
Yes, yes.
Fine. Mm-hmm. Does anybody else have any questions? Yes. One second.
Hello, I just have a small question. So to produce the filament, you use ASA and you mix it with non-metal metal powder. I just want to know, do you think that you could maybe reuse those parts, like recycle them and reuse them to make other circuits with something that has already been extruded with the printer? Or is the property loss too important that would like impact the efficiency of the conductivity, maybe.
You mean like recycling after
Yes.
one whatever component at the end of its life to recycle it and reuse?
Yes.
I'm not an expert. I'm more in the fabricating part, so I'm not in the material. But we are actually working on projects for this, and theoretically, this material could be recovered.
So adding maybe the metal powder to a recycled polymer might be
Yeah.
possible too.
Yes.
Okay.
Mm-hmm. Thank you.
How much does the layer orientation affect the resistivity of the printed material?
Well, I would like to have a concrete answer because we also were expecting this. But you've seen we've printed in different directions in this demonstrator, and so we thought maybe the square layers are like this will be good, and then when it goes up, that layers are like this, it will affect and it will increase the resistivity of that compared to the one that is on top. But it seems to not affect very much. So maybe the material really fuses well when it's deposited. And for example, the antenna, if this was a problem, because antenna is built layer by layer in this direction, so it will have problems. But it seems to work well in both directions.
Thank you.
You mentioned the resistance of this material. Could you tell us in percentage the resistance compared to copper?
I'm sorry, no, I don't have these numbers in my mind because I'm not in the part of this characterization. So but I can just ask my colleagues and have the answer for you. If you give me your card or whatever.
Yeah, fine.
I'm sorry.
No problem. Okay. Thank you.
Sorry.
Hi, thanks for the presentation. How high can you go in voltages? You showed like 0.8, 8 something. Can you go up to 100 volts with a low ampere or?
We haven't tested that, if how isolating is, or if it has problem breaking the material. We were more concerned about, because usually we work with low voltage applications, like for example the drone and capacitive sensors and antennas is mostly passive elements. So we haven't tested. We don't work in high voltage applications with.
And you're working with filaments, but did you also have the opportunity to work with resins, conductive resins, or do you know if they're?
So for resins, I think it's more complicated to have the conductivity because the formulation is more complex and the polymeric part, I think, has a higher weight in the final formula. My colleagues have been working a little bit on functionalizing resins, but the best result is in the FDM filaments. So we've been working on this, but we have also we can work on resins too. But the applications are result-oriented, so we don't have motivation to use the resin if the conductivity is lower. So we will use the FDM.
Thank you.
Any more questions? Perfect. Well, you can go to the 3D Evo stand in Hall 12.1 and see the parts. Thank you, Javier.
Thank you.
For your
Thank you very much.
presentation.
Thank you.